Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
If you take an ordinary plastic water bottle, right, and you drive out to the woods and just bury it in the dirt, it will sit there for, well, about 450 years.
Right. It's not going anywhere.
Yeah, the bacteria, the fungi, the entire biological machine of the forest will look at that bottle and essentially see a rock.
Exactly. To nature, it's completely alien.
But what if I told you that by next week, a vat of custom-designed, AI-generated liquid could dissolve that exact same bottle back into its original liquid building blocks in just 48 hours.
It sounds totally like science fiction.
It really does.
But we are actually moving into an era where biological recalcitrance, which is just the idea that nature simply cannot digest synthetic materials, is becoming an engineering problem rather than a permanent fact of life.
And that brings us to our deep dive today. Welcome, everyone. I want you, the listener, to just take a second and think about the last piece of plastic you threw away today.
Yeah, think about what it was.
Maybe a takeout container or a candy wrapper. Our mission for this deep dive is to explore how the fight against plastic pollution has fundamentally transformed. We are looking at a 2026 review document, and it's titled Generative AI, Metagenomics, and Process Intensification in Plastic Bioremediation.
Quite a mouthful.
Yeah, it is. But the takeaway is just huge. We are no longer, crossing our fingers and hoping nature eventually evolves the solution to our garbage. We are actively designing an industrial-scale circular economy.
We really are. And, the defining shift of this field in 2026 is the emergence of a complete design-to-deployment stack.
A design-to-deployment stack.
Right. For a long time, the approach was basically to stumble around in the dark, looking for a single naturally occurring enzyme that might, kind of degrade plastic if you squinted at it.
Like hoping you just get lucky.
Exactly. But now, researchers are merging generative protein design, massive environmental DNA mining, and these digitally controlled industrial platforms into one highly coordinated pipeline.
Okay, let's unpack this, because how do we actually do this? Break down a water bottle at the molecular level. I know nature uses enzymes, which are basically microscopic protein machines, to digest things.
Yeah, that's what enzymes do.
But if synthetic plastic is completely alien to nature, we can't just wait a million years for an enzyme to mutate on its own, right?
We don't wait anymore. We build them.
Wow, we just build them.
Yeah, we are using generative AI to design these enzymes entirely from scratch. We've moved from discovery to actual architecture. Generative AI has made the enzyme's internal framework, what researchers call the scaffold architecture, a variable that we can control.
Wait, I want to make sure I understand this. We aren't just taking a natural enzyme and tweaking it a little bit, like swapping out a part.
Not anymore. Researchers are using something called structure-first diffusion methods.
Okay, what does that mean?
Well, imagine you have a highly complex synthetic lock.
Yeah.
Instead of taking an existing skeleton key and filing down the teeth until it sort of fits.
Which would take forever.
Right. Instead of that, you show an AI the exact three-dimensional geometry of the lock's internal pins. The AI then generates the mathematical blueprint for a completely novel piece of metal that will perfectly engage those pins.
Oh, wow.
In biology, we give the AI the exact three-dimensional fold and catalytic geometry we want, and the AI generates the protein backbone to support it.
That's incredible.
Yeah, and then sequence design tools fill in the genetic code to actually build that physical structure in a lab.
Which makes sense because, these plastics are incredibly difficult materials. They're bulky. They're hydrophobic, meaning they violently repel water.
Which is a huge problem.
Right, since enzymes generally live in water. So it really is like 3D printing a custom skeleton key from scratch for a lock that nature has literally never seen.
It is. And that concept actually has a name in the literature. It's called zero-shot enzyme design.
Zero shot, like getting it right on the very first try without any practice.
Essentially, yes. It's the ability to generate a functional catalyst without having to iteratively train your model on every single specific target substrate. You achieve this by giving the AI structural priors.
Structural priors, you mean like giving the AI a hint about the shape it needs to make?
Think of it more as giving the AI the fundamental rules of the chemistry you want to perform.
Okay.
Like if you want to break an ester bond in a plastic, you tell the AI to pre-organize the active site of the enzyme, specifically for ester cleavage.
Ah, so you give it the baseline rules.
Right. By embedding those generalizable rules into the design process, you can propose a useful catalytic solution incredibly fast.
Right.
You dramatically shorten the timeline from, identifying a chemical target to holding a functional biocatalyst in a test tube.
I have to push back here, though.
Sure.
Biology is notoriously messy and unpredictable. Does this zero-shot design actually work in the real world or just in a pristine computer simulation?
That's a very fair question.
Because a beautiful 3D model spinning on a computer monitor doesn't have to survive a vat of hot, swirling plastic garbage.
And that is the crucial reality check.
Yeah.
What's fascinating here is that a computationally elegant design can still fail completely in the lab. Generative success demands physical realism.
Meaning, it has to actually exist in the physical world without breaking.
Exactly. When researchers do substrate docking in a computer simulation, where the software shows the AI-generated enzyme fitting perfectly onto the plastic molecule, that does not guarantee productive catalysis in real life.
Why not? Does the enzyme just, fall apart when it hits reality?
It frequently does, actually. It might suffer from solvent exposure, meaning the liquid it's floating in breaks it down, or it might experience oligomeric instability.
Oligomeric instability. Does that mean the different pieces of the engineered protein just sort of unravel and detach from each other?
Precisely. Remember, these depolymerase enzymes have to operate at a solid-liquid interface.
Right.
The enzyme is floating in a liquid solvent, trying to attack a solid chunk of plastic.
Which sounds difficult.
It is. At that physical boundary, things like polymer crystallinity, the surface roughness of the plastic, and how much the plastic chains can physically move around that matters just as much as the local chemistry.
So the AI is great, but it's not perfect.
Right. AI is a powerful discovery accelerator, but it isn't a magic wand.
Here's where it gets really interesting, though. If we have these incredibly advanced AI tools designing custom proteins, how are we actually doing with the plastic sitting in my recycling bin right now?
Right.
Because it seems like we have one massive success story, but I wonder if it's giving us a false sense of security. I'm talking about water bottles.
Ah, yes. You're referring to polyethylene terephthalate, or PET.
Right. From what I'm reading, we've made huge leaps with PET. We are using things called rationally designed, thermostable cutanese-like enzymes.
That's the one.
So let's break that down. Thermostable obviously means they can survive high heat, but what are they actually doing to the plastic?
Well, the heat is actually the secret to the entire reaction. These engineered enzymes can operate near the PET polymer's glass transition temperature.
The glass transition temperature, that's the point where the plastic stops being entirely rigid and glassy, right? Like it gets a little soft.
Exactly. It's the point where the rigid polymer chains start to gain a little bit of mobility. They start to wiggle.
Wiggle. I like that.
That's the best way to picture it. Breaking down PET isn't just a chemical problem, it's a materials problem. If the plastic is completely frozen and crystalline, the enzyme can't get in.
Oh, I see.
By engineering an enzyme that can survive in water that is hot enough to make the plastic chains wiggle, you improve the physical accessibility of the chemical bonds. The enzyme can physically reach its target.
Okay, so we can melt down water bottles. That's amazing. But if we have these super enzymes for PET, why are we acting like we've solved the whole plastics crisis? Isn't PET just the low-hanging fruit?
It is the absolute lowest hanging fruit available. And the scientific community is very careful to warn against using PET as a proxy for all plastics.
Because they're not all the same.
Not at all. PET has an ester backbone. Chemically speaking, ester bonds are pretty tractable. Nature actually knows how to break ester bonds already because natural fats contain ester bonds.
Oh, interesting. So nature has a head start there.
Exactly. But when you move to highly recalcitrant plastics, think of the polyurethanes used in foam cushions or nylons or silicones, you are dealing with a completely different universe of chemistry.
What makes a silicone spatula or like a foam cushion so much harder to dissolve than a water bottle?
Well, they don't have that easy ester backbone. Instead, they feature carbon backbones, high aromaticity, and intense steric shielding.
Steric shielding. I imagine that as a sort of molecular armor, like the bonds we want to break are physically hidden behind a wall of bulky atoms.
That is a perfect visualization. The target bonds are buried. The enzyme physically cannot reach them.
Wow.
And when you look at silicones, you're introducing entirely different bonds, like silicon oxygen and silicon carbon. You can't just use a simple hydrolase enzyme to cut those.
Because it's not the right tool for the job.
Right. You have to introduce oxidative chemistry or secondary accessory enzymes just to even make a dent. Breaking down a silicone requires an entirely different logical approach than breaking down plastic bottle.
So it's not a one-size-fits-all thing.
Not at all. Plastic bioremediation is a massive family of independent problems, not one universal reaction.
Okay. I'm genuinely lost on something then.
What's that?
If PD enzymes bounce right off of a silicone spatula, and nature doesn't naturally possess a blueprint for heavily armored carbon bonds, where is the AI getting its training data to build these new skeleton keys? It can't just guess out of nowhere.
It doesn't guess.
Yeah.
The AI gets its data from the very places we have polluted. We look to the plastosphere.
Wait, the plastosphere? Meaning we are literally digging through our own garbage to find the answer.
We really are. It's a process called metagenomic mining. Researchers are taking core samples from river sediments, landfill leachates, compost heaps, and industrial wastewater systems.
Just scraping the bottom of the barrel, basically.
Quite literally. They are extracting the raw DNA from the environmental microbiome that has been forced to adapt to human-made polymers over the last 50 years.
So they just scoop up dirt from a landfill, extract the genetic material, and run it through a computer.
Basically, yes.
But how do you look at millions of random DNA fragments and know which one codes for a plastic-eating enzyme?
That is exactly where the AI proves its worth. Because if you just search that landfill DNA for sequences that closely resemble the enzymes we already know about, you will miss all the truly novel solutions.
Right, because we're looking for something brand new.
Exactly. So instead, researchers use AI sequence embedding and structure prediction. This lets them detect what they call dark enzymes.
Dark enzymes, meaning they're completely invisible to our standard cataloging methods.
Yes. So a classical biological annotation pipeline, their genetic sequence looks like gibberish. It doesn't match any known protein family.
It's just noise.
Right. But the AI doesn't just read the genetic letters. It predicts the physical folding rules. It looks at the deep structural patterns and predicts, hey, this seemingly random piece of DNA from a landfill puddle actually folds into a 3D puzzle piece that could lock onto and degrade polyurethane.
Wait, so we are bioprospecting in our own waste, hoping a microscopic bug mutated a billion-dollar solution.
That's one way to put it, yeah.
But are these dark enzymes actually ready to use? Or are we just hoarding a massive catalog of theoretical DNA sequences on a server somewhere?
This raises an important question because the catalog itself is utterly useless without functional screening.
Okay.
Just because an AI sequence embedding suggests an enzyme might fold a certain way does not prove it will actually perform catalysis in the real world. The real breakthrough in 2026 isn't just finding the dark matter, it is the integrated workflow that follows.
You mean turning the computer model into an actual physical product?
Precisely. You combine the metagenomic mining with the AI ranking, and then you rapidly move to expression screening. You physically synthesize the protein in a lab, test its activity on real plastic, and then use short, iterative rounds of mutation to optimize it.
Wow, so it's a whole feedback loop.
It is. That workflow is how you turn a theoretical catalog of landfill DNA into a prioritized list of actionable industrial candidates.
Okay, let's play this out then. Let's say we've done it. We mined a dark enzyme from a landfill, used AI to optimize it into a perfect zero-shot catalyst, and it works flawlessly in a test tube.
A best-case scenario.
Right. Can I just spray a fire hose of this stuff onto a local dump and watch the plastic melt away?
I really wish it were that simple. This is perhaps the most sobering reality check in the entire field. The bottleneck today is no longer discovery.
It's not.
No, the bottleneck is deployment.
Because what works in a lab usually fails in a factory. I was reading about the contrast between a perfectly temperature-controlled 50-milliliter lab flask and a high-solids industrial reactor. I mean, in an industrial vat, you have mixed polymers, toxic dyes, chemical fillers. The trash coming in changes every single hour.
It's incredibly unpredictable.
And then there's the problem of mass transfer.
Mass transfer is an enormous hurdle at scale.
So, mass transfer basically means getting the enzyme to actually physically touch the surface of the plastic, right?
Yes, exactly.
I imagine it like trying to dissolve a solid sugar cube in a cup of freezing thick syrup without using a spoon versus dropping that same sugar cube into a hot cup of coffee and stirring vigorously.
That analogy captures the physics perfectly. In a tiny laboratory flask, you have the hot coffee and the spoon. You can easily agitate the liquid so the enzyme constantly collides with the plastic.
Right, it's easy.
But in a massive industrial reactor filled with a thick, sludgy slurry of melting garbage, physically moving the enzyme through that dense liquid to the target surface is incredibly difficult. The variables just explode.
Which is why we can't just rely on a magic enzyme. We have to engineer the environment around it.
Right. We call it process intensification. You have to create an entire ecosystem designed around the enzyme-specific needs.
What does that involve?
That includes calculating precise enzyme dosages, figuring out how to recover and reuse the enzymes, and, crucially, feedstock pre-processing.
Pre-processing, meaning what we do to the plastic before the enzyme even gets near it, like grinding it into a fine powder.
Or thermal softening to get it to that wiggling glass transition temperature we talked about earlier.
Ah, okay. That makes sense.
Yes, and to orchestrate all of this chaos, the industry is relying heavily on digital twins.
Okay, digital twins. These are digital models that provide feedback control to the reactors.
Right.
They integrate all these wild variables, the conversion speed, the viscosity of the sludge, the temperature, the mixing rate, to predict the throughput and optimize the whole depolymerization process.
They're incredibly complex systems.
But honestly, I have to ask, biology is famously temperamental. Does a computer model actually predict anything useful when the input going into the factory is quite literal, unpredictable garbage?
Well, digital twins do not solve the messy reality of biology. They manage the uncertainty.
Manage it how?
When you are dealing with heavily engineered AI enzymes, their performance envelope is often incredibly narrow. They need an exact pH and an exact temperature to survive.
So they're delicate.
Very. A digital twin takes real-time sensory data from the reactor and constantly adjusts the conditions, speeding up the mixing, tweaking the heat, adding a buffer to keep the entire process within that tiny window of survival.
Oh, wow.
If we connect this to the bigger picture, it is the only way to manage scale-up risk.
It's how you move from a cool pilot study that works once on a Tuesday to a commercially viable operation that runs every day of the year.
Exactly.
But even with the state-of-the-art digital twin and the perfect reactor, some waste streams are simply too complex, aren't they?
Unfortunately, yes.
I mean, real consumer plastic isn't just pure polymer. It's packed with chemical fillers, bright pigments, metal stabilizers, and toxic flame retardants. Pure biological enzymes must just choke on that stuff.
They absolutely do. Pure biology hits a hard limit against heavily engineered synthetic materials. And that brings us to the least mature, but arguably the most exciting frontier, bio-inorganic interfaces.
Meaning we stop relying purely on biology and start building, like, chimeric systems, cyborg enzymes.
It is a radical vision.
Yeah.
We're talking about combining biological protein scaffolds with inorganic chemical catalysts.
Okay, how would that work?
Well, if a plastic is loaded with heavy flame retardants, a delicate enzyme alone will not survive the exposure. But a hybrid bioinorganic system could use an embedded chemical catalyst to deactivate the toxic flame retardant or to crack open a stubborn chemical crosslink.
Sort of running interference.
Exactly, clearing the path for the biological enzyme to swoop in and finish depolymerizing the main backbone. It is a vital enabling technology for complex, dirty waste.
So what does this all mean? I want to pause here and highlight the critical outlook from the research, because there is a lot of hype in this space.
There is a massive amount of hype.
And the scientific consensus warns that many of the flashy degradation rates you see reported in press releases rely on highly favorable, perfectly clean lab plastics, not real, dirty, mixed waste from a curbside bin.
That's a very important distinction.
And they specifically highlight something called product inhibition as a massive barrier.
Yeah, product inhibition is a classic biochemical roadblock.
Is that when the plastic actually breaks down, but the resulting chemical soup gets so thick with debris that the enzyme can't find any fresh plastic to attack?
That is product inhibition in a nutshell. As the enzyme chops the plastic into smaller intermediate chunks, which we call oligomers, those oligomers build up in the liquid.
And they just get in the way.
They do. They eventually saturate the environment and physically block the enzyme's active site, gumming up the entire machine. And that leads to the most important warning we can discuss today.
Which is...
Depolymerization is not the same as true circular valorization.
Wait, so chopping a plastic bag into microscopic pieces is depolymerization. But if we can't actually do anything with those microscopic pieces, what have we accomplished? Are we just turning solid plastic waste into an invisible, toxic chemical sludge and calling it an environmental victory?
That is the profound danger of treating an enzyme like a magic bullet. If your industrial process breaks a plastic item down into intermediate oligomers, but you possess no economic or chemical method to recover those oligomers and repolymerize them into a brand new product.
Then you haven't fixed anything.
Right. You have not solved the pollution problem, You have simply changed the physical shape of the garbage.
You've just made the plastic invisible, which honestly might actually be worse for the water supply.
It could be. True success requires a full life cycle analysis. You have to measure the environmental and economic cost of the entire closed loop.
The whole system.
Harvesting the plastic, grinding it, heating it, deploying the enzyme, recovering the resulting chemicals, and manufacturing a new product.
That's a lot of steps.
And if the energy required to run that whole loop is worse than just making new plastic, the technology fails. We cannot simply cheer because an AI-designed enzyme showed some activity in a beaker. Partial progress is not full success.
Which brings us to the incredible synthesis of where we actually stand today. For you listening, the main takeaway is that in 2026, we have definitively moved beyond the simple, naive fascination of finding a plastic-eating bug in a landfill.
It is no longer a biological novelty.
Exactly. It's about integrating generative AI to design the perfect skeleton key, using environmental omics to scan the dark matter of the Earth for structural inspiration, and utilizing hardcore, digitally controlled process engineering to build the lock that the key fits into.
It is a single, highly complex functional bioprocess platform.
We are finally treating the plastic crisis with the scale and the engineering complexity it demands.
We are witnessing the emergence of an integrated discovery to manufacturing ecosystem. That is what makes this field scientifically credible today. We are no longer just asking if an enzyme can touch a piece of plastic. We're asking which specific plastics, under what intense industrial conditions, and at what total economic cost.
But I want to leave you, the listener, with a final thought to ponder something that builds on everything we've just discussed about this massive AI to reactor pipeline. If we are perfecting this digitally controlled system to instantly break down and recycle any synthetic material we throw at it, how will this alter the very nature of what we manufacture in the first place?
It's a fascinating question.
Will we soon see a world where consumer goods are deliberately built from temporary plastics, like materials specifically designed from day one with the biological keys already built into their molecular structure, just waiting to be triggered and eaten by our engineered enzymes on demand?
It would completely change the paradigm.
It changes our entire relationship with the physical objects we own. Thank you so much for joining us on this deep dive. Keep questioning the world around you, and we'll see you next time.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.